Hi, everybody. So today we're going to start a new unit, which is talking about stereochemistry. Okay. All right. So, all right, new topic: stereochemistry. One of the most fascinating aspects of organic chemistry is that the properties of a compound not only depend on how many carbons, hydrogens, nitrogens, not only depend on the elemental composition of the compound, but also how those elements, how those atoms are arranged in space. We saw this in an earlier situation when we were talking about the constitutional isomers, how the properties of the molecule depend on how the various carbon, hydrogen, nitrogen, oxygen, whatever atoms are linked together, resulting in different constitutional isomers, which will have different properties. Well, now we're going to take that another step further, and it's going to turn out that even though a molecule can have the same number of carbons, same number of hydrogens, oxygen, nitrogens, whatever, and arranged in exactly the same order of linkage, the same numbers and kinds of bonds, those molecules are going to have different properties anyway. Okay, so I brought a little model here. And so this model, it's a carbon atom there in the center. And that carbon atom is bonded to a green ball, an orange ball, a blue ball, and a white ball. So green, blue, white, and orange. All right, so here's another molecule. And it's also a carbon atom in the center here, bonded to a green ball, a white ball, an orange ball, and a blue ball. It's the very same thing as our first model. So these guys, these are not constitutional isomers. They are constitutionally identical. They are bonded to the same, they have the same formula, and their atoms are linked together by the same number and kinds of bonds, atom for atom. But what we're going to see in this lecture and in a few more lectures to come up is that these guys are not identical structures. They are constitutionally identical, but they are not identical structures, because we define identicality in organic chemistry as the ability to superimpose one molecule on top of another, right? We don't like to use the word same. We don't like to say that two molecules are the same, because that word same does not have this precision that we need to make these fine distinctions. Okay, so these two guys have the same numbers and kinds of bonds, but the ultimate test of identicality is whether they can be superimposed one on top of the other. If I can lay one molecule on top of another and get everything to match up, then they are identical. So, okay, so I'm going to try to do that now. Okay, so now I'm superimposing the blue ball with the white ball. See how the blue ball and the white ball have matched up, but the orange ball and the green ball are not matched up. They're goofed up. Okay, so now let me try to superimpose the green ball and the orange ball. Okay, so there, I fixed that problem. Now the green ball and the orange ball superimposed, but now the white ball and the blue ball, they're goofed up. See, I have a blue ball over here and a white ball over here. That's not matching up. I have a blue ball over here and a white ball matching over here. They're not matching up, but the green and the orange match up. So these two guys, even though they are constitutionally identical, even though they have the same formula and the same numbers and kinds of bonds. Both of them are a carbon atom bonded to an orange ball, a white ball, a green ball, and a blue ball. They are not identical structures. So that is the one of the thrusts of the unit that we're getting into now about stereochemistry. And a very important concept that we deal with when we talk about stereochemistry is the concept of chirality. Okay, so first of all, let's get the pronunciation of this very important word correct. That CH at the beginning, that is a hard K sound, chirality. Please do not say chirality. Right? It's chirality. And the reason that that is a hard K sound is that this is the transliteration of the ancient Greek word for hand, which is hair, which has a hard, sort of a hard K sound at the beginning. Okay, chirality. The adjective is chiral, right? And please do not say chiral. Right, the adjective is it's chirality and chiral. And chirality, this is the property of having a non-superimposable mirror image. All right. And so this is going to be a big focus of what we're going to be talking about for the next couple of lectures. Okay, so now the reason that this word chirality is derived from the ancient Greek word for hand is because your hands are the chiral objects par excellence. Okay, so there's my right hand. And now imagine, drop a mirror here, and here's my left hand. My left hand is the mirror image of my right hand, right? You could see that there's a mirror here, and the thumb on one hand is reflected to the thumb of the other, and so on and so forth. So these are mirror images of each other, but they are non-superimposable mirror images. If I try to lay my right hand on top of my left hand, oh, that didn't work. You see how my thumbs are goofed up now, and my fingers are goofed up. My index finger of one hand is below the little finger of the other. Okay, so now let's try to do it that way. Well, that's not superimposition either, because one hand has the palm facing up, whereas the other hand has the palm facing down. They do not match up. Your hands, your left hand and your right hand, these are the chiral objects par excellence. They have they are non-superimposable mirror images. And so they are not identical, right? They're very similar. They both have a thumb and a total of 5 fingers, a palm, a back of a hand, all of that. They're very similar. They're constitutionally identical, but they are not identical structures. And one of the things that we know about just from daily life about our hands that is going to translate into the behavior of organic molecules is that you can do stuff with your right hand that you cannot do as well with your left hand, right? You can write or crochet or whatever it is you do with one hand better than you can with the other hand. So it's going to be the very same thing with molecules, is that we have what we will informally call right now right-handed molecules, and you have what we will informally call right now left-handed molecules, and they are very similar, but they're not identical. And the right-handed molecule or the left-handed molecule can react in ways that are different and different from the way that the opposite molecule can do. All right, so that's what's going on with these molecules that I showed you a little a little while ago is that these are non-superimposable mirror images of each other. So imagine you have a mirror right here. Let's see. Yeah, okay. So now you have the mirror right here, and this white ball is the mirror image of this white ball. This green ball is the mirror image of this green ball. The orange ball and blue ball, these are all mirror images of each other. But they are non-superimposable mirror images, as we just saw. I can get the green ball and the orange ball to match up, but I can't get the blue ball and the white ball to match up. So these guys, they're chiral. This guy right here, he's chiral. He has the property of having a non-superimposable mirror image. This guy, he's chiral. He has the property of having a non-superimposable mirror image. So getting back to this definition, everybody remembers the mirror image part, right? But people tend to forget the non-superimposability part of this definition of chirality. Everything has a mirror image except a vampire, but chirality does not mean whether it has a mirror image. Chirality means whether that mirror image is non-superimposable or not. Okay, so let's look at some, so the ultimate test of chirality is this. We would look at the object, we would draw its mirror image, and we would see whether the object and the mirror image are superimposable or not. Okay, so if we imagine a circle, is a circle chiral? This is the object, right? And now let's drop a mirror here. That's the mirror. That's the mirror. And this circle looks at itself in the mirror and it sees that, right? So this is the object and this is the image. So is a circle chiral? Does it have a non-superimposable mirror image? Oh, heck no. I can pick up this object and lay it on top of this image and get everything to match up. So this thing is not chiral. And so we have a vocabulary word for that. So we can say that this guy is not chiral. It has a superimposable mirror image. And the specialized vocabulary word is, we say that a circle is achiral. All right, so that's a word that I do not like to use, because you say, well, something is achiral, and you're thinking, well, it's achiral what? But, you know, that's just a vocabulary word. I frequently say non-chiral because I don't like this word achiral. So a circle isn't chiral. It has a superimposable mirror image. Okay, so let's see. Let's look at some pictures for a second. Oh dear. Okay, so we're going to be doing a whole lot of looking through the looking glass, just like Alice, right? There's Alice, there's her image, and there's the mirror. Your hands are the chiral objects par excellence. Your left hand is the mirror image of your right hand, but they are non-superimposable. They're very similar, but they can't. But they're not exactly the same, because we define identical structures as superimposable, right? Now, this guy here, all right, this object, and there's the mirror, and there's its mirror image. And we see that when you stand like this, anyone out there besides me do yoga? Yeah, when you stand in your Tadasana, in your mountain pose, you are not chiral. You are achiral. Because we see that I can lift this image, object and lay it on top of this image and get everything to match up. Okay, let's see. Is this something that I want to pay attention to? Okay. All right, so the ultimate test of chirality is this. You look at the object, you draw a mirror, you look at the image and see whether they're superimposable or not. Okay, that's all very well and good, but we need something more efficient than having to draw a structure, twice. So we have some quick and dirty tests for chirality. So I'm going to give you the test for chirality, and then we'll talk about them. Okay, so tests for chirality. If to be chiral, a molecule, an object, it doesn't have to be a molecule, it can be a cup, it can be your body, it can be whatever. To be chiral, a molecule cannot have a center of symmetry. Well, what the heck is that? Well, we're going to talk about that. What exactly is a center of symmetry? So if something has a center of symmetry, it cannot be chiral, right? Just going to lay down the law, and then we'll go back and talk about all of this stuff in nauseating detail. Okay, to be chiral, a molecule cannot have a plane of symmetry. Okay, what's that? We'll talk about what a plane of symmetry is, but if a molecule or an object or your body or whatever has a plane of symmetry, it can't be chiral. Third quick and dirty test of chirality is if a molecule has one and only one chirality center, comma, that molecule is chiral. So no plane of symmetry, no center of symmetry, but if the molecule has one and only one chirality center, it is guaranteed to be chiral. All right, and what is a chirality center? We'll be talking about that. Okay, so these are the quick and dirty tests for chirality. Let's unpack all of those tests. And the general topic that I'm talking about now is that of the symmetry operations or the symmetry elements. Now, maybe some of you have taken advanced math. Maybe you've heard of group theory, right? That's an advanced branch of math. This is an application. What we're talking about now is an application of group theory to organic chemistry. And that application is brings up the symmetry operations or the symmetry elements. And we're going to be dealing with three symmetry operations. Okay, the first one is this, the first symmetry operation is the center of symmetry. All right, so now this is given the group theoretical symbol I. All right, so just because center of symmetry takes a long time to say and to write, it's frequently abbreviated with the symbol I. And what exactly a center of symmetry is, if you want the exact definition, we could say that if a molecule has a center of symmetry, it is invariant to reflection. Well, that's just more gobbledygook. Okay, so finding a center of symmetry is easier than defining what it is. And so here's what you do when you're looking for a center of symmetry and whether a molecule has one. Imagine yourself standing at the center of the molecule and you look out in one direction and you hit an atom or group. Now, if you look in the exact opposite direction, same distance, exact opposite direction, do you hit an equivalent atom or group? And no matter where you look in the molecule, if you look exactly behind you, same distance, will you hit an equivalent atom or group? That molecule has a center of symmetry. Okay, so let's look at an example here. If we look at benzene, right? When we're talking about benzene and we're discussing its symmetry elements, it is much better for you to use the so-called Robinson formulation of benzene rather than the Kekulé structure of benzene. In other words, when we're talking about symmetry elements, use the benzene ring with the little circle, with the circle inside and not the double bonds. This is totally legitimate because we know that those double bonds in benzene are not really double bonds, and those single bonds in benzene are not really single bonds. Because of resonance, those bonds are all somewhere in between being a double bond and a single bond. So when we're talking about benzene and symmetry, use this formulation of benzene. Okay, and so now I'm going to decorate this benzene with hydrogen, and I'm going to look for a center of symmetry. I'm here in the middle of the molecule. I'm standing here in the center of the molecule. Okay, there I am. I'm going to look up. I hit a carbon atom. Now I'm going to look in the exact opposite direction, same distance. I hit a carbon atom. Okay, I'm standing here at the center of the molecule. I'm going to look toward 2 o'clock, and now I'm hitting a hydrogen. Okay, and now I'm going to look in the exact opposite direction, same distance. I hit a hydrogen. Okay, so things are looking pretty good right now. Okay, I'm here at the center of the molecule. I look out in this direction. I look out in this direction. I hit a carbon atom bonded to a hydrogen, sp2 hybridized. I look in the exact opposite direction. I hit a carbon atom bonded to a hydrogen. No matter where I look in the molecule, if I look in the exact opposite direction, same distance, I will hit an equivalent atom or group. Benzene has a center of symmetry. Is benzene chiral? Oh my heavens, no. Because if a molecule has a center of symmetry, it cannot be chiral. So here's now the ultimate test of chirality with the mirror. There's benzene, Robinson formulation. There's the mirror. Benzene looks at itself in the mirror, and what does it see? It sees that. Can I pick up the object and lay it on top of the image and get everything to match up? Sure I can. Benzene, this is not chiral, right? It has a superimposable mirror image because it has a center of symmetry. Another thing I'm telling you is there are no left-handed benzene molecules and no right-handed benzene molecules. All benzene molecules are identical to all other benzene molecules, right? So this is the implication that this is going to have, is that there aren't different kinds of benzene molecules, one that can knit or write better than the other one can, the way you can with your left hand and your right hand. All benzene molecules are identical. They all react the same way. They all have the very same properties. Okay, so We get into the habit of liking to drop the mirror between the object and the image, but that's not where the mirror has to be. That is not required. We can also imagine this situation where we have the benzene, there's the object, and now instead of dropping the mirror here, what I'm going to do is I'm going to drop the mirror over here. This benzene looks at itself in the mirror and it sees that. There's the object. There's the mirror. I'm trying to get you away from thinking that the mirror always has to be between the two structures. It doesn't have to be. There's the object. There's the object. This is the image. The object and the image are superimposable. They have superimposable mirror image. Benzene has a superimposable mirror image. It is not chiral. Okay, so that's the center of symmetry. That's the first symmetry operation. Next symmetry operation is the plane of symmetry. And again, that takes a long time to say and to write, so it is usually denoted by this group theoretical symbol, which is sigma. Lowercase Greek letter sigma, again, an unfortunate choice because we have, sigma can stand for a lot of things in chemistry, bonds, for example, but this is just what we call it. Okay, now what is a plane of symmetry? This is a mirror plane that you drop through the center of the object, whether it's a molecule or not. You drop through the center of the object, and is the left the mirror image of the right? Is the top the mirror image of the bottom? Is the back the mirror image of the front? Okay, so if it does, if the molecule has a plane of symmetry, it can't be chiral. Okay, so instead of trying to draw something like this, let's go maybe here. Let's look at some of these pictures. Okay, right here, you see, there I am standing in my Tadasana, in my mountain pose, and I have a plane of symmetry. I drop the mirror plane through the middle of my body, and I see that the left is the mirror image of the right. My right eye is the mirror image of my left eye. My left nostril is the mirror image of my right nostril, my right arm, my left arm, so on and so forth. Oh, and in case you were wondering, yes, I posed for this silhouette. I guess you can see that perfect V development of the upper body. Yeah, so I posed for that. So this is a plane of symmetry. It says that the left is the mirror image of the right, or the top is the mirror image of the bottom, so on and so forth. Okay, so now this molecule here, cis 1,2-dichlorocyclopropane, it has a plane of symmetry. The left is the mirror image of the right. I drop this mirror plane through the middle of the molecule, through the center of the molecule. The green ball looks into the mirror, it sees the green ball. The black ball sees a black ball. The hydrogen sees a hydrogen. This hydrogen in the back here, the left-hand side of this hydrogen is the reflection of the right-hand side of the very same hydrogen. So yeah, this molecule has a plane of symmetry. And we talked about how when you stand in your Tadasana, you don't have, you are not chiral. You have a superimposable mirror image because in that posture, you have a plane of symmetry. So let's just write this down. What is a plane of symmetry? This is a mirror plane. This is a mirror plane that is passed through the center of an object. And the questions that you're asking yourself, is the left the mirror image of the right question, or is the top the mirror image of the bottom, or is the back the mirror image of the front, and so on. And if you can answer any of these questions in the affirmative, the molecule, the object, has a plane of symmetry and cannot be chiral. Okay. The third and final symmetry element that we're going to be considering, this is the axis, the axis of symmetry. Okay, so the axis of symmetry, this is, if a molecule, if an object has an axis of symmetry, that has no bearing on the chirality. But we need to talk about all of these symmetry elements now, because next week when we get into nuclear magnetic resonance, NMR, we're going to need all of these symmetry elements again. So this is just the most efficient way to discuss these symmetry elements. But in an earlier page, I showed you the symmetry elements that have bearing on chirality, the center of symmetry and the plane of symmetry. The axis of symmetry doesn't have bearing on chirality, but let's talk about it anyway, because we're going to need to talk about it eventually. Okay, so this is the most most common symmetry element, but it is also devilishly hard to find in a molecule. And so the axis of symmetry, this is denoted by the symbol C sub n, right? That's the group theoretical symbol. And what that n means, if a rotation of the object by 180 degrees results in the same before and after picture, then that molecule, that object, has what is called the C2 axis of symmetry. So you see this N, this is actually 360 degree divided by whatever, divided by N, and that gives the degree and the degree measure of the rotation. So everything has a C1 axis, because when you take anything, there's my pen, I'm going to rotate it by 360 degrees somehow. Oh, that's the very same before and after picture. So everything has a C1 axis. But if you have an object, molecule, whatever, rotated by 180 degrees, do you have the same before and after picture? Then that molecule has a C2 axis of symmetry. Okay, so let's see. Let's look at an example here, because the symmetry operations is quite confusing. There's the water molecule, right? Let's say that's oxygen, that's hydrogen, that's the water molecule. I'm going to rotate this by 180 degrees. My pen here is illustrating the axis of the rotation. Here goes, rotate by 180 degrees. Check that out. See what that molecule looks like, right? That's the before picture, rotated by 180 degrees. Looks exactly the same. Water has a C2 axis of symmetry. So that is how we're looking for these axes of symmetry. But then we have axes of order higher than 2. If a rotation by 120 degrees results in the same before and after picture, then that object, that molecule, has a C3 axis of symmetry. And what does that 3 mean? That means 360 divided by 3 means 120-degree rotation resulted in the same before and after picture. Then that is the C3 axis. So this rotation, an axis of symmetry, we can also define that as invariant to rotation, just like the center of symmetry is invariance to reflection. Okay, a rotation by 90 degrees and you have the same before and after picture, that's the C4 axis, and so on and so forth. Okay, so that's the axis of symmetry. And again, just to repeat, the presence of an axis of symmetry has no bearing on chirality, but we need to talk about all of these symmetry elements now anyway. Okay, so we have the symmetry operations under our belt, and now let's look at a bunch of examples, a bunch of molecules where we're trying to find whether the symmetry elements are present and whether that molecule is chiral or not. Is it going to come in a left-handed version and a right-handed version? Or are all of these molecules going to be equivalent? Okay, what about the water molecule? All right, so here's our water molecule. Tell me in the chat, does water have a center of symmetry? You're standing in the center of the molecule, you look out. You hit an atom or group. Now look in the exact opposite direction, same distance. Do you hit an equivalent atom or group? Does water have a center of symmetry? 1 in 2 chance of being right just by guessing. Does water have a center of symmetry? Oh my heavens, no. Right, you're here at the center of the molecule, maybe here somewhere. You look in this direction, and now you look in the exact opposite direction, same distance. Maybe you're looking over here. There's no hydrogen there. No, so water doesn't have a center of symmetry. Okay, water, no center of symmetry. Okay, the next symmetry operation is the plane of symmetry. Okay, and so now the question's a little bit more complicated now, because a molecule can only have one center of symmetry, but a molecule can have multiple planes of symmetry. So look at this water molecule and tell me, how many planes of symmetry does it have, right? The question is no longer, does it have a plane of symmetry? Because I'm telling you that a molecule can have multiple planes of symmetry. How many planes of symmetry does the water molecule have? Yeah, water has 2 planes of symmetry. And so we denote that as 2 sigma. All right, so where are the planes of symmetry in water? Well, the easiest one to spot is maybe this one, up and down, that says that the left is the mirror image of the right. But water has a second plane of symmetry, which says that the top is the mirror image of the bottom, right? The water molecule sits on a tabletop, and the top, the part of the water molecule that is above the table, is the mirror image of the part of the water molecule that is below the plane of the tabletop. So water has 2 planes of symmetry. Is water chiral? Oh, heck no, because there are no left-handed water molecules and right-handed water molecules. All water molecules are identical because the molecule has a plane of symmetry. Right? To be chiral, a molecule can't have a center of symmetry, nor can it have a plane of symmetry. Water has a plane of symmetry. In fact, it has 2. All right, so now we go to the fearsome C2 axis of symmetry. the axes of symmetry, and we already saw how water has a C2 axis of symmetry, which means it's invariant to rotation. You see you twirl the molecule around 180 degrees. You see the same before and after picture. It has a C2 axis of symmetry. Okay, so now check this out with this water molecule. See this guy right here? See this hydrogen right here? That's Fred. Okay, that's Fred, right? See this guy right here? That's Mary. Okay, so did you memorize who Fred is and who Mary is? Okay. Okay, which one is Fred? You have no idea which one is Fred, right? Because of the symmetry of the molecule, right? Is Fred there or is Mary there? You don't know. So these two hydrogens are symmetry related. They're symmetry equivalent. They are equivalent by a plane of symmetry. They're also equivalent by an axis of symmetry. Okay, so those are the symmetry elements of water. Now let's go to something a lot more complicated. So if you're playing along, if you're taking notes, if you're playing along, if you're being good, let's copy down this molecule and good luck to you. All right, so let's see, I'll give you some guidance. Draw an equilateral triangle. And now a second equilateral triangle, which is behind this first equilateral triangle, right? So I have two triangles like that, and now connect the dots, connect the dots, connect the dots. How about a little square down here, and another little square here, and another square down there, connecting the dots, something like that. Okay, so the systematic name of this molecule is about that long, but it has a very cute common name, trivial name, nickname. So tell me in the chat what you think a very nice common name would be for that molecule. What does it look like? The okay, right? But you know, does it have any of the, does it have a priority group in it? Do you see a carboxylic acid or an ester or an amide or a, no? So this thing, its common name is housane, right? It looks like a house, it's called housane. Tell me all the symmetry elements of housane. Does it have a center of symmetry? Does housane have a center of symmetry? Oh, and this is a real molecule. It was synthesized in the 1970s by Professor Albert Padua of the Ohio State University. So does housane have a center of symmetry? You're here at the center of the molecule. You look up, you see the roof. You're here at the center of the molecule. You look down, you also see the roof. How many drinks have you had? So does housane have a center of symmetry? No, no center of symmetry. Okay, and now let's look at the planes of symmetry. And again, when it comes to planes of symmetry, a molecule can have multiple planes of symmetry. So tell me in the chat how many planes of symmetry, if any. How many planes of symmetry does housane have, if any? The correct answer may be 0. So you're telling me in the chat how many planes of symmetry? Okay, whoa, I see all kinds of answers here. Housane has 2 planes of symmetry. Okay, the plane of symmetry that's maybe easiest to spot is the plane of symmetry that says the left is the mirror image of the right. So we have a plane of symmetry. So I'm using this red pen. I don't know if this is going to show up in the Zoom. And so we have a plane of symmetry that says that the left is the mirror image of the right. Where's the other plane of symmetry? It is perpendicular to this plane, right? So the second plane of symmetry is somewhere here, right? So there are the two planes of symmetry. So for example, let's say this is the front door and this is the back door. You have a plane of symmetry that comes in the front door and cuts through the house and exits the back door. You have another plane of symmetry. Maybe this is the kitchen window and maybe this is the bathroom window. You have another plane of symmetry that cuts in the kitchen window, goes through the house and exits out the bathroom window. So you have two planes of symmetry. Okay, so now the fearsome axis of symmetry, right? These axes of symmetry, these are the hardest symmetry elements to find. But they are also the most common. The C2 axis of symmetry is the most common symmetry element, but it is devilishly hard to find in many cases. And not only that, but a molecule can have multiple C2 axes. A molecule can have multiple C2 axes and then also C3 axes or C4 axes to boot. So tell me about housing. Does it have a C2 axis? Or how many C2 axes does it have? Right? The answer here is not yes or no. The answer is how many C2 axes? Okay, I think it's going to have one C2 axis. And it's going to have one C2 axis. Whoa. It's going to have one C2 axis that maybe cuts in the roof and exits the floor. And so a 180-degree rotation results in the same before and after picture. So Haussmann has a C2 axis of symmetry. Does it have an axis of symmetry of order higher than 2? Does it have a C3 axis, or does it have a C4 or a C5 or something like that? Well, it turns out that it doesn't, right? So those are the symmetry elements of Haussmann. Is it chiral? Nope, it's not chiral because it has a plane of symmetry. Okay, so ready for something really hard now? Let's talk about the symmetry operations of benzene. And remember, when we talk about benzene and symmetry operations, we're always looking at this Amit-Robinson formulation, the hexagon inside the square. Okay, so now tell me about the symmetry elements of benzene. Does it have a center of symmetry? Yep, we already talked about that. It has a center of symmetry. Now let's talk about planes of symmetry. How many planes of symmetry? The plane of symmetry is a plane that you drop through the center of the molecule. And does it say the left is the mirror image of the right, or the top the mirror image of the bottom, or the back the mirror image of the front? How many planes of symmetry does benzene have? Tell me here in the chat. How many planes of symmetry? Well, I haven't seen the right answer yet. Okay, still not seeing it. Ah, there it is. 7 planes of symmetry. So if we look at benzene over here, here's a plane of symmetry that says the left is the mirror image of the right. And notice what that plane is doing. It's cutting through opposite carbons. Here's another plane of symmetry. And notice what it's doing. It's cutting through these opposite carbons in benzene. That's a second plane of symmetry. And here's a third plane of symmetry. Okay, so that's 3 down. Now let's redraw this benzene because it's getting quite ugly and quite messy. Okay, now another plane of symmetry that's easy to spot is a plane of symmetry that bisects opposite bonds. But here's another plane of symmetry that bisects opposite bonds. And here's yet another plane of symmetry that bisects opposite bonds. So 6 down. But there are 7. Where's the 7th plane of symmetry? Tell me in the chat. Benzene has 7 sigma. Where's the 7th and remaining plane of symmetry? The plane of the paper, right? Benzene is flat, is sitting on a tabletop. The part of the benzene molecule that is above the tabletop is the reflection of the part of the benzene molecule that would be below the tabletop. So just on a piece of paper, if we want to show that, we call that the molecular plane. That's the molecular plane. And maybe we could draw a bracket around that. That's usually how it's drawn. So those are the 7 planes of symmetry. 7 planes of symmetry. Okay, so now let's go to the axes of symmetry. So that means a rotation of 180 degrees is going to give you the same before and after picture. That's C2. Rotation of 120 degrees, same before and after picture, invariant to rotation. That's C3, so on and so forth. So tell me about the C2 axes of benzene, if it has any. How many does it have? Yeah, so here, tell me in the chat, how many, if any, C2 axes? You're rotating the molecule by 180 degrees. Do you have the same before and after picture? How many C2 axes, if any? Okay, lucky 7 is not the right answer, so let's try again. Oh, benzene has 6 C2 axes. And just by sheer accident, they are collinear with the planes of symmetry. So benzene has 6 C2 axes. All right, so again, let's find them. All right, so this C2 axis here, that's easy to spot, right? This rotation of C2 of 180 degrees, the C2 axis brings the left to the right, the right to the left. It also brings the top to the bottom. This would be another C2 axis right here. For benzene, the C2 axes, just by accident, there is no correlation between the number of planes of symmetry and the number of C2 axes. This is just for benzene. So there are 3 C2 axes that way. And now, here's another C2 axis this way. If you twirl the molecule that way, the C2 axis brings the top to the bottom and the bottom to the top. So there's a C2 axis, but here would be another C2 axis, and here would be yet another C2 axis. Right, so this has 6 C2 axes. Does benzene have an axis of symmetry of order higher than 2? Does it have a C3 axis or does it have a C4 axis? Does it have an axis of symmetry of order higher than 2? And if it does, tell me what is its order. Oh, benzene has a C6 axis. 360 divided by 6 is 60. So benzene has a C6 axis of symmetry. It has a C6 axis of symmetry. And if we take the benzene molecule and lay it on edge, right? There's our benzene molecule. Our C6 axis of symmetry is perpendicular to the plane of the molecule. There's the C6 axis. So 360 divided by 6 is 60. If you twirl the benzene molecule by 60 degrees in that direction, you have the same before and after picture. It has a C6 axis. So has lots of symmetry elements. Okay, I'm going to take a break now, but I want you to look at these molecules while I'm gone, and I want you to figure out there's housane, we just did that, right? Here's a Newman projection, right? There's a chair. This is prismane, and this is a nitrile. We're going to talk about the symmetry elements here after our break. My computer says 9:57. I'll be back at 10:10. Okay, we're back. So hope that you were practicing finding the symmetry elements of some of those molecules. Want to look at the symmetry elements of this cyanogen, systematic name ethane 1,2-dinitrile. Okay, so does it have a center of symmetry, right? There's my little model of the molecule, right? These are the carbons and the white balls can be the nitrogens. So does cyanogen have a center of symmetry? Oh, heavens, yes, right? Has a center of symmetry. You're here in the center of the molecule. You look in one direction, you hit carbon, triple bonded to nitrogen. You look in the opposite direction, you see an equivalent atom, right? So this has a center of symmetry. Is it chiral? Oh heavens, no, it has a center of symmetry. What about planes of symmetry? So how many planes of symmetry in cyanogen? Maybe here you could tell me in the chat. How many planes of symmetry? 2, 3, oh, more than that. It has an infinite number of planes of symmetry. So cyanogen has infinite number of planes of symmetry. So with this molecule here, with this model here, I mean, it's easy to see, like, so there's a plane of symmetry that cuts down the middle of the molecule. It says that the left is the mirror image of the right. Okay, so that's a plane of symmetry. But now if you look at the molecule on edge, we look at the molecule on edge like this, like I'm holding the model here, we see that there's a plane of symmetry that says the left is the mirror image of the right. Let's try to orient this model like that, right? You see there's a plane of symmetry that says the left is the mirror image of the right. And so here's the plane of symmetry that we just saw. But now I'm going to take this molecule and I'm going to rotate it 1/1,000,000th of a degree. There's a new plane of symmetry. The one we just found was over here. Now here's another plane of symmetry that says the left is the mirror image of the right. Now I'm going to rotate this molecule 1,000,000 bazillion degrees. Right? There's another plane of symmetry different from the one we saw before. So this molecule has a plane of symmetry there and there and there and there and there and there. They're all, you know, lots and lots, an infinite number of planes of symmetry. Okay, what about C2 axes of symmetry? How many C2 axes of symmetry does the cyanogen have? It has an infinite number of C2 axes of symmetry, an infinite number of C2 axes of symmetry. So you're going to rotate this 180 degrees and come up with the same before and after picture. So here my pen, that's the C2 axis rotated 180 degrees. I see the same before and after picture. But if I rotate this molecule any number of degrees, I have a new C2 axis. So this molecule has an infinite number of C2 axes that are kind of like a ruff around the center of the molecule. It has an infinite number of planes of infinite number of C2 axes. What about axes of symmetry of order higher than 2? Does it have any axes of symmetry of order higher than 2? Yeah, it has a C infinity axis of symmetry. And, okay, and so where is that C infinity axis? It lies along the bond axis. So see, I'm going to rotate this molecule. The C infinity axis is here where my pen is. There's the C infinity axis. I'm going to rotate this molecule a millionth, a bazillionth of a degree. It's the same before and after picture. And now I'm going to rotate this molecule a million, bazillion, gazillion degrees. It's the same before and after picture. So this has a C infinity axis of symmetry. Okay. So if you look at my lecture notes online, you'll see that there's a lot of practice problems there finding axes of, the symmetry elements. Okay, so returning to an earlier page, we already discharged the symmetry elements, and now let's talk about this. If a molecule has one and only one chirality center, it is guaranteed to be chiral. So let's talk about what is a chirality center. Chirality center is an sp3 hybridized atom. It doesn't have to be carbon. It could be nitrogen. It could be, there's chirality carbon, there's chirality nitrogen, there's chirality boron, there's chirality silicon. It doesn't have to be carbon, but it has to be an sp3 hybridized atom that is bonded to 4 non-equivalent groups, right? I'm not saying 4 non-equivalent atoms. There's a difference. I'm saying 4 non-equivalent groups. That's what a chirality center is. And if a molecule has one and only one chirality center, then it is guaranteed to be chiral. All right, so let's look at a simple example. So there's a carbon atom. I'm going to make this a chirality carbon atom. It's sp3 hybridized, and I'm showing the dash and wedge picture. And up here, I'm going to put F. Up here, I'm going to put Br. Here, I'm going to put H. And here, I'm going to put, let's say, maybe CH3. Okay, that's a chirality center. This guy right here, he's a chirality center. And now look at this molecule. Is he chiral? He has one and only one chirality center. Is he chiral? Well, yes, because does this molecule have a center of symmetry? You're here in the center of the molecule. You look up, you hit fluorine. Now you look down. Do you also hit fluorine? No. This doesn't have a center of symmetry. Does it have a plane of symmetry? Is the left the mirror image of the right? Or is the top the mirror image of the bottom? Or is the back the mirror image of the front? Is that a plane of symmetry? Here, no. Br looks into the mirror and it wants to see another Br, but here it's looking at a methyl group. Is that a plane of symmetry? No. Is that a plane? No, it doesn't have any planes of symmetry. It's chiral. And the thing that it's chiral because it doesn't have a plane of symmetry, doesn't have a center of symmetry. It also has one and only one chirality center, which is an sp3 hybridized atom bonded to 4 different groups. Okay, so now let's look for chirality centers. Okay, this is premature. All right. So any So this is the molecule menthol, right? It's the compound that's responsible for the flavor and aroma of mint. We find this in a lot of different places in daily life. Anytime you have a minty flavor in anything, in toothpaste, chewing gum, Vicks Vapor Rub, anywhere you have a minty flavor, this has there's probably menthol in there. Tell me how many chirality centers it has. Tell me here in the chat. Right, you're looking for an sp3 hybridized atom that is bonded to 4 different groups. How many chirality centers? sp3 hybridized atom bonded to 4 non-equivalent groups. So how many chirality centers in menthol? Tell me here in the chat, how many chirality centers? Okay, so the responses are all over the place. You're looking for an sp3 hybridized atom. How many bonded to 4 non-equivalent groups? How many? There are 3 chirality centers. Okay, so let's hunt around for this molecule looking for the chirality centers. Well, the 12 o'clock carbon, that's a chirality center. This is a chirality center right here because it's bonded to a methyl group. This carbon atom is sp3 hybridized. It's bonded to a methyl group. It's bonded to a hydrogen. Oh, can't forget about him, right? He's bonded to a hydrogen. And on the left, he's bonded to CH2. And on the right, he's bonded to CH2, but keep going, right? That's a CH2, that's a CH2. Is this road equivalent to this road? It is not. CH, jump out 1 carbon, you hit CH2, keep going. You hit CH2, and now you hit something that's not a CH2. Right, so even if you have to jump out 1,000,000 atoms to establish the non-equivalence of those 4 groups, you must do so. Right, the road in the clockwise direction is different from the road in the counterclockwise direction. That's a chirality center. It's bonded to 4 different groups, 4 non-equivalent groups. Okay, so where's another chirality center? Here's another chirality center here at 4 o'clock. He's bonded to an OH group. He's bonded to a hydrogen, can't forget about him. He's bonded to a CH2, and he's bonded to something that's not a hydrogen, that's not an OH group, and that's not a CH2, right? That's another chirality center. Where's the 3rd and final chirality center? It's down here at 6 o'clock. He's bonded to a hydrogen. He's bonded to a fishtail. He's bonded to a CH2. And he's bonded to something that's not a hydrogen. That's not a fishtail. That's not a CH2. That's the 3rd chirality center. Okay, so let's try again. So I'm just going to draw this molecule freehand. It's going to be a chair conformation because we have to be able to find chirality centers regardless of how they are presented. So let's see, fat bond here, fat bond here, fat bond here. An axial methoxycarbonyl group. Anybody recognize this molecule? Maybe tell me in the chat. Oh, it's something you've all heard of. Anybody recognize this molecule? Just out of curiosity, it's not important really. Give you a big clue. You want the clue again? Oh, it's cocaine. Circle the chirality centers in cocaine. How many circles are we looking at? You're looking for an sp3 hybridized atom that is bonded to 4 non-equivalent groups. How many chirality centers in cocaine? Yeah, so here, tell me in the chat what you're coming up with. Circle the chirality centers. How many circles are we looking at? I think there's going to be five chirality centers. Okay, so let's look for the chirality centers. Well, this one is easy to spot right here. This guy down here, he's a chirality center. He's bonded to this, looks like an ester group over here. Bonded to a hydrogen, can't forget about him. He's bonded to a CH2, and he's bonded to something different going there to the back of the molecule along that skinny bond. So that's a chirality center. What about this guy right here? Is he a chirality center right here? Oh no, because he's bonded to 2 hydrogens, right? So that's not 4 non-equivalent groups. Where's another chirality center? Well, there's another chirality center right here, right? He's bonded to an equatorial hydrogen. He's bonded to this methoxycarbonyl group. He's bonded to this affair down here in the front. And the road to the left is different from all of the other 3 groups. So that's a chirality center. Here's a chirality center as well. Here's another chirality center here. Okay, so that's 4 down. Where's the 5th and final chirality center? Tell me in the chat. Where's the 5th and final chirality center? It's the nitrogen atom. He's bonded to 4 non-equivalent groups. And what is he's bonded to a methyl group. He's bonded to the front of this molecule, which is totally different from the back of the molecule. And what is the 4th and final group here? His electron pair, right? So there's chirality carbon, there's chirality silicon, there's chirality nitrogen, there's chirality all kinds of stuff. And one of the things that becomes apparent is that most of the molecules, or a lot of the molecules that are most important for biochemistry and for organic chemistry, are loaded with chirality centers, right? Cocaine has 5 of them, right? That's an important molecule. A carbohydrate will have many chirality centers. DNA has billions of chirality centers. Your average protein is going to have dozens or hundreds or thousands or even millions of chirality centers. So the most important and the most interesting molecules in organic chemistry and in biochemistry are loaded with chirality centers. Okay, so let me give you another problem here. How many chirality centers in this molecule? Tell me in the chat. How many chirality centers? Most popular wrong answer, 1. This thing has 0 chirality centers because to be a chirality center, an atom has to be sp3 hybridized. And we know that this nitrogen atom has an unshared pair of electrons that we can move around in resonance. It has a steric number of 4, but because it has this unshared pair of electrons that we can move around in resonance, it has 0 chirality centers because this nitrogen is sp2 hybridized, right? We were talking about how hybridization impacts how resonance impacts hybridization. That nitrogen's not sp3 hybridized. It can't be a chirality center. Okay, so another example that would be very similar to that would be something like this. How many chirality centers there? Is that nitrogen a chirality center? No way, because it has an unshared pair of electrons that can be moved around in a legitimate resonance structure. Its steric number is 4, but because it has that unshared pair that can be moved around in resonance, this nitrogen atom here is also sp2 hybridized. So can be tricky, right, with nitrogen. All right, so that's what a chirality center is. And so we got some practice in finding chirality centers. All right, now what I want to talk about now is, this organic chemistry is science. And one of the hallmarks of science is that everything gets a name, everything gets a designation, everything gets a unique designation. I don't know, have you ever taken anatomy? Anatomy is also a science. And when you cut in to your cadaver there and read your textbook, you see that every muscle has a name. And it's usually some kind of freaky Latin name, right? And every bone has a name. And every little hump on a bone has a name. And every little declivity, dippy down part of a bone has a name. And this is one of the hallmarks of science, is that everything gets a name. If you want to turn surfing into a science, the first thing you need to do is figure out a name for everything. Your posture on the surfboard, what the different names and unique names for the waves, all kinds of names are required. Okay, so that is what, that's one of the hallmarks of science. Everything gets a name. And the chirality center is not exempt from this requirement of science. Is that up to now we've been talking about left-handed molecules and right-handed molecules, but that doesn't have the precision that we need because sometimes molecules have many chirality centers, as we just saw. So we designate the chirality of a chirality center. That's what I want to talk about now, using the Kahn-Ingold-Prelog RS system, right? This is the nomenclature of the chirality center. And this is called the Kahn-Ingold-Prelog. Well, that takes a long time to write and say. It's three guys that got together in the 1950s. Kahn, I'm not really quite sure who he was. Ingold, Christopher Ingold, this was a very famous organic chemist from Cambridge University. And Vladimir Prelog, this is a Nobel Prize winner. He's the father of the modern birth control pill. So instead of saying Kahn-Ingold-Prelog, we usually say the CIP-RS system. Okay, and this is how we designate the chirality of a chirality center. So what I'm going to do is I'm going to lay down the law, and then we can work some examples. Okay, so here are the steps. Step number 1, find the chirality center. Right? I'd hate for you to be wasting all kinds of time trying to figure out the chirality of something that wasn't a chirality center. So that's the first thing you do, find the chirality center, and we got some practice in finding chirality centers. Okay, step number 2 is now you rank the atoms directly bonded to the chirality center. In order of atomic number, high to low. So it helps to memorize the periodic table, but normally we always have access to a periodic table, so there's no need to memorize the periodic table. So that's the second step, is you rank the atoms that are directly bonded to the chirality center in order of atomic number, high to low. But you know what? I need to put an asterisk here because later we'll see, put a little asterisk here, later we may need a tiebreaker. But we'll talk about that later. So right now, let's just keep things nice and simple. And let's say we don't need that tiebreaker. We're just ranking the atoms directly bonded to the chirality center, high to low. Okay, step number 3. Here's the killer, right? This is the hardest step here, is now you orient the chirality center. You orient the chirality center. So the group or the atom, so the atom of lowest rank points away from you. That's the hard part, right? If you have zero visualization skills, you're going to have to use models. But what you want to be able to do is to look at the model, and in your imagination, you want to be able to orient the chirality center so that the group of lowest rank, or the atom of lowest rank, is pointing away from you. That's the killer. All right, now we're fourth and final step. A clockwise sweep of the top 3 ranks, that chirality center is said to have the R absolute configuration, right? Not conformation, but configuration. So the clockwise sweep of the top 3 ranks with the chirality center oriented so that it is facing away from you, that has the R absolute configuration. This R comes from the Latin word rectus, which is a fancy way of saying the right hand. Okay, a counterclockwise sweep, that is said to have the S absolute configuration, which that S comes from the Latin word sinister, which is a fancy way of saying the left hand. Okay, so that's the Kahn-Ingold-Prelog RS system. This is how, instead of talking about right-handed chirality centers and left-handed chirality centers, or right-handed molecules or left-handed molecules, we use this R and S designation. Okay, so let's do some examples. Something really simple to start off with, right? Okay, so now if we go back to this molecule, maybe we saw him before. All right, so we saw that that's a chirality center. Furthermore, this molecule is chiral because it has one and only one chirality center, so it's going to be chiral. We want to designate the chirality of its chirality center, and that's what we use the CIP system for. There's our chirality center. Now I'm going to rank the atoms directly bonded to the chirality center in order of atomic number high to low. So I'm looking at a periodic table and I see bromine is going to be rank number 1. Fluorine is going to be rank number 2. Carbon is going to be rank number 3, and hydrogen is going to be rank number 4. Okay, and now with the group of lowest rank pointing away from me, oh, I gave you this problem on a silver platter, right? You see how that hydrogen is pointing away from you. What is the sweep of the top 3 ranks? I'm going from 1 to 2 to 3. That's a counterclockwise sweep. That is the S absolute configuration. And the official name of this molecule would be 1S, right? That's the stereochemical descriptor that we find in the, as the very first part of a systematic name. This 1 is telling you the number of the carbon that has the S absolute configuration. 1S, 1 bromo, 1 fluoroethane, right? That would be the official name of this molecule, where I'm throwing in the chirality of the chirality of the chirality center. Okay, so now if we look at this guy, see what I did now is I switched up the location of the Br and the CH3. And now let's determine the chirality of this chirality center. And so we're ranking everything by atomic number high to low. And now with the group of lowest rank facing away from you, pointing away from you, which it is here. So this is an easy easy problem. We notice the sweep of the top 3 ranks. We go from 1 to 2 to 3, and now this is a clockwise sweep. So this would be called 1R, 1 bromo, 1 fluoroethane. These aren't constitutional isomers. They're constitutionally identical, but they are not identical molecules because one of them has the R absolute configuration and the other one has the S absolute configuration. One of them, if you want to talk informally, is the right-handed molecule and the other one is the left-handed molecule. Okay, so these are, those are some easy examples there. Okay, so now let's look at, let's stay here. And now let's look at some examples where maybe not so easy, right? The killer is orienting the group of lowest rank so that it is facing away from you. Okay, so let's try to figure out the chirality of something like this. Okay, so tell me in the chat, did you find the chirality center? Yeah, I hope so. Tell me whether that is the R or the S absolute configuration. And you know, as hard or as difficult as these problems can be, and some of these can be very hard, you have a 50-50 chance of being right just by guessing, right? So when questions like this appear on the quiz, you know, you have a 50-50 chance of being right. Just put an R down there, 50-50 chance of being right because it could only be R or S, right? All right, so this is going to turn out to be the R absolute configuration. All right, so let's see how we came up with that. So there's the chirality center. It's bonded to 4 different groups. Now we're going to rank the atoms directly bonded to that chirality center in order of atomic number, high to low. So chlorine is 1, oxygen is 2, this carbon down here is 3, and hydrogen is going to be 4. And now with the group of lowest rank facing away from you, but it's not, right? The group of lowest rank is pointing right at you. What do you do now? Well, you have a lot of different things that you can do. So, you know, if you have excellent visualization skills, maybe you can take this molecule and maybe either on a piece of paper, you can pancake flip it. You can pancake flip it like that. And when you pancake flip it like that, now that has fixed everything, right? This chirality center, when you pancake flip it like that to put that hydrogen on a dash, now that hydrogen is now over, that chlorine was in the back, you pancake flipped it, it's now in the front. That hydrogen was in the front, you pancake flipped it, it's now in the back. Oh, and now this is 1, this is 2, this is 3, this is 4, and now the group of lowest rank is facing away from you. And so we see, this is easier to see, you go from 1 to 2 to 3, that's an R absolute configuration. Okay, so that's one thing you can do. Maybe if you have excellent visualization skills, you don't even need to do that. Another little trick is when the group of lowest rank is facing you, which is what it's doing here, when the group of lowest rank is facing you, note the sweep of the top three ranks, but recognize that you're looking at the molecule backwards. The group of lowest rank is supposed to be pointing away from you. Here it's pointing toward you. Note the sweep of the top three ranks and then reverse it for the right answer. So with the group of lowest rank facing me, pointing toward me on this wedge, I'm going from 1 to 2 to 3. It looks like a counterclockwise sweep, but I'm looking at the molecule ass backwards. The group of lowest rank is facing me. It should be pointing away from me. Reverse the sweep for the correct answer. So this counterclockwise sweep actually translates into this R absolute configuration. So that's another little trick that you can do. You should be able to do all of these just by inspection and in your imagination. You shouldn't have to be writing anything, right? That's where we want to get. If you have no visualization skills, you have to use models. All right, now let's go to the next level of complication. What about determining absolute configuration maybe on a chair? Right? Because we have to be able to determine these absolute configurations regardless of how the molecule is presented. All right. That's going to need the tiebreaker. Let's try again. Fat bond, fat bond, fat bond. All right, so there's our chirality center. Tell me about that chirality center. Tell me in the chat, is it R or is it S? Okay, well, it looks like I'm getting the R absolute configuration here. And again, the rankings would be the Cl is 1, the oxygen is 2, this carbon back here is 3, and this is 4. And in this chair conformation, the group of lowest rank is neither pointing away from you nor pointing toward you, right? It's in the sort of like in the plane of the paper, pointing straight down. Now what do you do? Well, again, you have many techniques at your disposal. One of the skills that we have worked on is the ability to translate a chair into a dash and wedge drawing. So that's something that you could do as well here, is that we know how to translate chairs into dashing and wedging. Remember, your eye is up here. You're looking down on the chair. This chirality center here, the hydrogen is down. So that's going to be on a dash. And the Cl is on the top of the molecule. That's where you are. And so this is the dash and wedge drawing of this chair. And it's just easier to determine absolute configuration with dashing and wedging than it is from a chair from a Newman projection. So I translated this chair into this dash and wedge. I see 1, 2, 3. I'm getting R. 1, 2, 3. Yeah, I'm getting the R absolute configuration. But you want to develop great visualization skills, right? And you shouldn't have to redraw a molecule. You should be able to determine the absolute configuration just from the figure that you are given. And so I imagine myself here, I'm looking down on this molecule. The group of lowest rank is pointing away from me. If my eye is up here, and now I'm noting the sweep of the top 3 ranks, And it's clockwise. Yeah, that's the R absolute configuration. So, you know, we have these visualization skills are here at a premium. All right, so let's see. On an, let's try, how about let's try an R and S on a Newman projection. Sure, why not? Okay. That carbon in the back, is he a chirality center? Oh, heck no. He's bonded to 3 equivalent hydrogens. The chirality center is the carbon in the front. So tell me about that chirality center. Is that the R or the S absolute configuration? Have you memorized the periodic table? So that that carbon in the front is a chirality center. Is it R or S? All right, that's going to be an S absolute configuration indeed. So there's a chirality center. Let's rank everything. Bromine is 1, chlorine is 2, oxygen is 3, and the group of lowest rank is going to be the carbon that is hidden behind this disk, right? It's the group of lowest rank is not always going to be a hydrogen. In this case, it's that carbon that is hidden behind that disk. So very conveniently, the group of lowest rank is pointing away from you, right? It's going into the page of the, it's going into the page. And so all we need to do is note the sweep, go from 1 to 2 to 3. The group of lowest rank, which turned out to be that carbon, is pointing away from us. That's the S absolute configuration. How about let's do one more, another Newman projection. We need to be able to figure these out regardless of whether it's, however it is written. So let's see, how about if we put H there, Br there, Cl there, and H there. Okay, so now tell me about that chirality center. That's the carbon in the back. What is its chirality? Is it R or is it S? Okay, so this is going to be, I'm getting the R absolute configuration. And so the rankings will be bromine is 1, chlorine is 2, this carbon here in the front, he's 3 and hydrogen is 4. And now with the group of lowest rank facing away from you, pointing away from you, in other words, I'm going to put my eye here, and I'm looking at that carbon in the back with the hydrogen pointing away from me, and I have pretty good visualization skills. And so what I see is bromine is down here, and then I'm moving up to 2, and then I'm moving to the carbon in the front. So I'm getting an R absolute configuration there as well.